Anyone
This
have
conference will now be recorded.
anyone have any questions so far? And just type them in the chat. Cool. I'll keep checking back. Awesome. Okay, so yeah, as I was saying in the last picture there, because in a warm front, since the cold air is the one that's really retreating from the warm air, a warm front will resemble that kind of long, gentle slope we see in the bottom right picture here. And then in a cold front, since it's really the cold air that's moving and advancing on this lighter warm air, the cold front looks like a steep bulge there. So we also have another phenomenon called occluded fronts, and basically, if you remember back to this picture on this slide, frontal systems are circular, right? They move around the center of low pressure. So you have part of this front is a cold front, right, with the blue triangles that are advancing like rather fast. But then you also have this part of it with the red semicircles, the warm air that's retreating. That's coming up behind the back of this cold front essentially at a lot slower rate. And basically what happens is in an occluded front, these, if you can think about it just looking at this picture, what happens is the blue triangles almost kind of catch up to the red semicircles, and you have what's called an occluded front. So look what's happening in this picture here. You have in the bottom right there, you have cool air. So it's part of the cold air mass, right? But it's almost if you can imagine this frontal system moving in a circle, it's basically the back of what's on the left here, this cold air that's advancing. So basically this cold front has gone all the way around this frontal system and has caught up to the warm air that's advancing on the back of it, right? And so what happens is, you get this occluded front, right? You almost have three different air masses in terms of temperature that are all converging. And so then you have all this warm air that all of it just gets moved straight up, as you can see there. Yeah, so it's an occluded front or an occlusion. Okay, so a couple definitions. So a frontogenesis is a front which is increasing in intensity. So typically a cold front, right, because they tend to be more unstable, right? And just the word there, the good way to remember it is genesis. So that word is a biblical term you might have heard, which means like the beginning, right? So frontogenesis, a front which is increasing in intensity. So like it's just started and it's getting stronger. And then we have frontolysis, so that's a front, that's just the opposite of front, which is decreasing in intensity. So that'll probably happen after the occlusion happens. So the cold air is advancing, frontogenesis is getting stronger, it goes all the way around this frontal system, and then it basically catches up to its own tail, right? It meets this cool air, right? It forces all the remaining warm air up into the atmosphere, and the temperature gradually stabilizes again. So that would be frontolysis. A squall line is a line of thunderstorms that sometimes accompanies the passage of a cold front, right? And remember, because cold fronts tend to be a lot more unstable, right? You have a lot of air that's rising, which is a big requirement for thunderstorms to form. You need a lot of air and a lot of moisture rising in the atmosphere very quickly to form those strong kind of thunderstorms. So yeah, cool. And then, so this little table here just shows the kind of weather changes you can expect as a front passes. So for wind in a cold front, you can expect it to veer, which means the wind changes direction clockwise. And then for a warm front, you can also expect veering, but not as fast as a cold front. The temperature, obviously, for a cold front, it would gradually drop because it's cold. And then in a warm front, you would expect a gradual rise. And then for visibility, you have poor visibility as it passes, right? And that's typically because you get bad weather, like the squall lines of thunderstorms. And so when a warm front passes, you'll get improving visibility, right? Because you've moved out of that area of typically more unstable air with bad weather into an area with more stable air. In terms of pressure, you get a decrease in pressure as it approaches, but you get a sharp rise once it passes. And then the reason for that is because, like I said before, cold air is a lot denser and a lot heavier than warm air. So once that cold front passes and now you're under an area of a cold air mass rather than a warm one, you're going to feel more pressure. And then a warm front, non-significant, and then the reason for that is just going to be because you've come like at the back of the area of cold air where it's almost stabilized with the warm air, so there's not going to be a very significant rise. The most significant difference between the cold part of a frontal system and the warm part is going to be at the cold front, where you have the big bulge of cold air advancing onto the warm one. And then in both types of fronts, they'll be somewhat turbulent, probably more likely at a cold front, again, just because it's so unstable. But in any kind of weather system where you're changing very suddenly between moisture content, pressure, right, everything you see here, wind, there'll always be, of course, a certain amount of turbulence. Precipitation in a cold front will be narrow, and it'll usually just be at the boundary, so like right at the front. And again, that'll be the types of squall lines you'll see, right? So if we look at the cold front here, it'll just be at the boundary, right? Because you have this very pronounced change, right? This big bulge that's coming in. And then for a warm front, it'll be long and pronounced, and the reason for that's pretty intuitive, right? Like look in the picture in the bottom right here. Look at that, even the little graphic of that cloud going over a very large distance, just because it's such a long, narrow, gradual slope. So if there is any clouds above, it'll tend to be over a longer distance there. So that's how to know if you think you have a front approaching. Okay, so now let's talk a bit about different types of precipitation that we can have. Also important to know. So precipitation is, as you guys probably know, is when water droplets in a cloud grow enough so that gravity causes them to fall to the ground. Right? Because a cloud is basically just a condensed form of water vapor, right? But then when it gets heavy enough, that water vapor changes back into a liquid and falls to the ground. So yeah, so as they grow, all these tiny little water particles in the cloud, they coalesce with each other, right? They join onto other parts of liquid, and once they get heavy enough so that the water vapor in the cloud can't hold on anymore, it basically just lets go of it due to gravity. And so radiation, it's important to know the different types of precipitation that you encounter. So drizzle is just very light rain, very small water particles, right? So that'll probably be if you have a decently unstable cloud actually, right, or a low cloud, that's when you'll probably get more kind of drizzly rain, right? And then the reason for that is because the water droplets are falling from the cloud at a smaller size, right, rather than typical rain, it probably means there's more wind or it's more unstable or that sort of thing. Then we have rain, which is our basic large water droplets. We can have hail, which I'm sure you guys know what it is, but what it's made up of is basically it's super cooled water droplets that freeze onto ice crystals, and is essentially so if I'm sure we all know the freezing temperature of water is 0 degrees, but what can happen up in a cloud is that if it's stable enough, if the cloud is stable enough, what can happen is that water droplets, even when they go below 0 degrees, they won't freeze immediately, right? But when they're disturbed by, let's say, an ice crystal that's also in the cloud, then they'll freeze extremely quickly just around an ice crystal. And so that's what hail is. So it's a neat phenomenon. So sometimes water doesn't freeze at 0 degrees if it's very, very stable enough. And then we have snow, which is just water droplets that are above 0 degrees, and they freeze directly into ice crystals. So that's the difference between snow and hail, if you've ever wondered. Cool. And then another important thing to know in aviation is fog. So fog is basically just a cloud that's at surface level. So it's stratus cloud, which is just clouds that form in a nice, stable, uniform layer. So it's just stratus cloud that touches the ground, essentially. So we have 6 types of fog, and they're classified by how they form. So first we have radiation fog, which occurs at night when the ground is cold. Right? Because during the day, the way the atmosphere gets its heat is the sun's rays heat the ground, and then those in turn, the sun rays radiate off the ground and warm the atmosphere. So at night, when the ground stops receiving those rays from the sun, the ground gradually gets colder before the air above it does, because the air actually is the last to be warmed by the sun's rays, right? Because it's radiation off the ground. So yeah, basically the ground gets cold, and then the ground, which is now cold, makes the air directly above it colder. And so if there's moisture in this air and it's cold enough and stable enough, then you'll get fog that forms, radiation fog. We have advection fog, which is when warm air drifts over a cold land or sea surface. And then it gets cooled below the dew point, right? And the dew point is the temperature at which the atmosphere or the air can no longer hold water vapor, and it starts condensing into a cloud, in this case fog. And then we have upslope fog, so air that's cooled by expansion as it moves up a hill, right? Because as air rises, it gets colder, right? Hot air rises, and as it does, it gets colder. And that's called orographic lift, as air moves up a hill or a mountain. We have steam fog, which is when cold air goes over warm water, and then because now you have you have cold air over warm water, what that basically does is it forces the water to evaporate until the cold air is saturated. And so the way I'd always remember this one is that's basically what happens if you've ever been like in a hot tub or even a pool during the winter time, and you see steam rising from it. That's basically, or even when you're cooking, that's essentially steam fog too, if you have relatively colder air over very warm water or relatively warmer water. Second last one, precipitation-induced fog. So that's when rain falls from a warm section of air, and basically what happens, it just evaporates before it hits the ground directly back into the atmosphere, and that's what that is. And then lastly, we have ice fog, and so you'll see this in winter. I've seen it like flying in the winter before. Basically what happens is when it has to be very cold, the air has to be very moist, but also very calm. And essentially what happens is you have a sudden addition of moisture. So like when you turn a plane's engine on, for example, there's like a burst of air and moisture that comes out from the engine, and you might see a bit of a cloud form. That's what ice fog would be. So the saturated air basically immediately can't hold anymore. So that new moisture sublimates directly into a mini cloud, basically. Okay, so now let's talk about a couple of definitions in terms of visibility. So haze in aviation, of course, is also important to know. And haze is basically just very small particles. It can be water, salt, dust, dirt, any impurity. And that forms a uniform layer that blocks visibility. So you can't see the individual particles with the naked eye, but from a distance, it'll block your visibility. So visibility itself, in terms of flying, the definition, quote unquote, is the distance at which prominent objects may be seen and identified by day and prominent lighted objects by night. So when we talk about flight visibility, that's the average range of visibility that you can see forward from the cockpit of an airplane in flight. Slant range visibility, that's the distance a pilot can see over the nose of the airplane towards the ground. And so that's not something that is impacted by weather. That can just be as simple as moving your seat forward in the plane so you can see over the nose better, that sort of thing. We have ground visibility, which is so in a weather report, for example, which are recorded at airports, this is what you'll see. So that's just the visibility when you're on the grounds at an airport. Prevailing visibility is, so right, like let's say you're standing somewhere and you look around in all directions. There might be more visibility in one direction and less in another direction. Prevailing visibility is the average visibility for over half of what you're looking at, so half of the horizon. And then lastly, we have runway visual range, which is the distance in hundreds of feet that you can see down the runway, right? So sometimes in weather reports, if you have crappy visibility, they'll specifically mention this, right? Because runways at big airports can be over a mile long, right? So sometimes when visibility is under a mile, they'll feel the need to report the runway visual range as well. Yeah, one of the worst aviation disasters in history actually happened when a 747 started taking off on a runway. You might have heard of it, the Tenerife disaster. And basically, they could only see halfway down the runway because the weather was so bad. The runway visual range was very low. And there was another 747 taxiing across that runway at the same time another one was taking off. And so they couldn't pull up in time and they hit each other, which was very bad. So yeah, always important to know what kind of visibility you're dealing with. Okay, let's just run through this. And sorry, let me just, can I get a time check? Officer Cadet Mode, we have till 7:30 in total, right? And you have your lesson as well?
That is correct. You have both periods tonight.
I have both grades tonight, till 7:30?
Yeah.
Oh, okay. Okay, gotcha. Okay, sorry, let me just look at the chat. What front is higher pressure? Cold front, because it's higher density. Oh, there you go. You guys heard about the KLM crash? Yeah, no, it was, if you guys ever watched like Mayday or something, you might have seen it. Okay. Actually, you know what? I think now would probably be a good time to let you guys take a break. I know we've been going for about half an hour now. I don't want to fry your brains too much. But then when we come back, we'll finish off this PowerPoint. If we have some time, I have another one that I can show you guys. We can talk about weather reports and that sort of thing to finish off. So how about we take a break until about 7:15 or so, and then we'll come back and finish off air masses. And if you have any questions during the break, just throw them in the chat as well. All right, guys, 7:15. Let's get started again. Finishing off talking about air masses and weather. Back to the PowerPoint. Perfect. So as always, if you have any more questions, just toss them in the chat. Okay, so let's talk about VMC and IMC. So VMC, so visual meteorological conditions, means that distance from cloud, visibility, and ceilings are better or equal to the minimum required to meet visual flight rules. Okay, so I'll read out the definitions and I'll tell you what they mean in terms of the law and everything for flying. And then IMC, it means that visibility, distance from cloud, and ceilings are less than minimum required for VFR, and you can only fly instrument flight rules. And so what that means for aviation is this. So for VFR, visual flight rules, means that the weather is good enough where you can fly the plane with primarily by having reference to what's outside the plane, right? So what that means is you can see the ground well enough that you don't have to only be looking at the instruments inside of the plane in order to fly. That's basically what it means. And then for IFR, if you're flying under instrument flight rules, that means you can only look at what's inside the cockpit in order to fly the plane, right? And you might think, oh, isn't that what you always have to do? But for VFR, so when you get like a basic pilot's license, like how we do through cadets, what they tell you to do for the basic private pilot license, which is just VFR, you're supposed to look outside of the plane 80% of the time and only be looking at your instruments for 20% of the time, because your primary reference in terms of what the plane is doing should be looking at the ground. Like, are you in a turn, for example? You can look outside and see if the horizon is sideways, right? That sort of thing. Are you going up or down, right? You would look at, okay, how is my nose pointed relative to the horizon? And then you would cross-reference or check that based on the instruments you have inside of the plane. So when you're flying IFR, which is essentially an addition onto your pilot's license, that means you've reached a level where you can be flying and not even looking outside at all, right? It basically means you're good enough so that you can only be looking at your instruments and know exactly what the plane is doing, right, to a good extent. And so obviously what that means, if you have a VFR license, the weather has to be pretty good when you go flying at a basic level, right? You have to be far enough away from clouds. The clouds have to be high enough. That's what ceiling means. And the visibility has to be good enough, right? You have to be able to see outside and to the ground and all that. So for IFR, obviously that opens up a lot more options in terms of the types of weather you can fly in. So all airline pilots, for example, would be able to fly IFR, right? So you can fly through a cloud, for example, or land while it's raining and the visibility is really bad, because all the reference you need is inside of the cockpit for IFR. Cool. Awesome. So now let's talk about thunderstorms. So thunderstorms obviously are an extreme weather event that pose a big risk to flying, right? You have a lot of instability, a lot of precipitation, you have lightning that can hit the plane. That can be a problem, of course. So yeah, not something that's good for us as pilots. So to form a thunderstorm, you have three basic requirements, which I think I touched on before the break. So you need unstable air. You need some form of lifting action. So the air has to be rising somehow, because air only condenses once it gets to a certain temperature, so above the earth. And you need high moisture content, because you need water vapor in the air to condense into these water droplets, which of course form clouds and precipitation. So there are three stages of a thunderstorm. You have the beginning stage is a harmless kind of cumulus cloud, so like a puffy white cloud. But then gradually, as this cloud gets more and more moisture in a very, very small time frame, and there's a lot of lifting action that's kind of keeping this cumulus cloud all as one big connected entity, even as it moves really high into the atmosphere, it becomes a cumulonimbus cloud. And so for those of you in ground school, you remember nimbus means is something at the end of the name of a cloud that means a cloud from which precipitation falls. That's what nimbus indicates. So then you get to the mature stage as an intense cumulonimbus storm. And then eventually, as with all clouds, eventually it just gets rid of all of its precipitation and it'll dissipate back into first like the cumulus clouds, and then eventually it'll just get rid of all the moisture inside of it. So there are two main types of thunderstorms in terms of how they form. So you can have air mass thunderstorms, and they form usually on hot summer days in warm, moist air. And the main distinction for them is that they're usually very isolated. So you'll have, often you'll have perfectly clear weather around these thunderstorms, but within them they'll be very isolated and very intense. And so the reason for that is because in the summer, when you have a lot of sun rays bouncing off the earth at very uneven levels, the conditions in one very isolated area might be such that you're getting the exact amount of lifting action because of those thermals radiating off from the surface of the earth, and the moisture content's perfect as well, so you'll get a very isolated thunderstorm, right? And with that being said, they'll be easier to avoid because the weather around them will usually be pretty decent. The second type of thunderstorm is a frontal thunderstorm. And you'll remember before the break when we talked about squall lines in an advancing front, usually a cold front, right? And so the reason for that is because you have a very, very long extended area of a very sudden change in moisture, in temperature, right? And so that obviously means instability, which is one of the requirements for a thunderstorm, right? And so the reason why these are so dangerous is because obviously, remember we said how fronts and air masses can be, almost an entire continent across, right? So they can be a very, very long line of thunderstorms. And because you get a lot of clouds in general that form at the intersection between two different air masses, so a cold and a warm, you might not be able to tell that there's a thunderstorm forming in what might look like just an overcast sky of cumulus clouds. So those can be pretty dangerous, as opposed to air mass thunderstorms, which you can typically tell are forming in a very isolated way. Cool. And then dangers of a thunderstorm. So obviously turbulence, right? Very unstable air, lightning, which is not always a good thing. But, it's never a good thing, but it's not always fatal, right? Like the big airliners, for example, they can typically withstand being struck by lightning at this point now. But if you're in a little plane, probably not the best situation. But the thing is, it's not always necessarily bad so it can knock out your electronics, but it won't make the plane catch fire or anything like that typically, because for that to happen, if with anything in electricity, for it to have a really bad effect, it has to be grounded somehow, right? So that's why they typically say even cars aren't at risk, because if a car gets struck by lightning, for example, the rubber absorbs electricity very well. And so in a plane, because you're never, and when you're flying, you're not touching the ground, obviously, that electrical current has nowhere to get grounded. But it's still not good. It can still knock out your electronics just from a big surge in electricity, even if it's very sudden. You can get hail, of course, another bad type of precipitation, which can cause, obviously physical damage to the plane. You can have icing, which is very bad. So we talked about this recently in ground school. Icing, if you have ice forming around your antennas, for example, that can knock out your communications. If you have ice forming on the windshield of the plane, that'll block your visibility, of course. But the biggest danger is if you have ice forming on the wings of the plane, what can happen is that the shape of the wing gets changed by this ice to such a degree that the wings can't produce lift anymore. And so the plane literally can't fly, which is not a good thing. In a thunderstorm, you can also get really rapid pressure changes, obviously, especially in a frontal thunderstorm where you're getting that anyway because of the change from warm to cold air mass or vice versa. Severe wind, of course, that goes hand in hand with turbulence, and severe rain, which can damage your plane, obviously blocks visibility, so very important to avoid thunderstorms. Cool. Okay, so yeah, here's a bit more about icing, right? So yeah, as it just says there, and as you can see in the picture, that's just when water droplets condense onto a onto an airplane, right? And typically it's super cooled water droplets. So remember, it's water that's suspended in the air as like within a cloud, and even though it might be below zero, right? So freezing range, because these water droplets are suspended and they're not being disturbed by anything else, they won't freeze, because essentially they'll be warmer within the water droplet relative to the outside of the water droplet. So they'll only freeze once they get disturbed by some outside force and they get all mixed up, and then they're exposed to the freezing temperatures. And so obviously that can happen if you fly a plane through them, right? And you have a big wing just smashing through all these super cold water droplets, and then they'll immediately freeze and condense onto the first thing around them, which, if you're unlucky, will be your airplane. So yeah, a few dangers of icing. I mentioned a couple of them, but also a couple others I didn't mention. So blocking the air intakes for the instruments, right? Because the instruments in the plane, they rely on readings of the atmosphere from outside of the plane. So the ground school, you guys will remember this. The pitot tubes, the static ports, where a lot of the air goes into the plane to give a reading for the instruments. So how fast you're going, your altitude, that sort of thing. If you have ice forming inside of them, then it might block that air intake, and then you'll get an inaccurate reading on your instruments, which can be very dangerous, of course. In a propeller plane, it can really damage the propeller if you have ice forming on it. And the carburetor, which is basically something within the engine that regulates how much fuel goes into the engine. If you have, ice going in there, that can really damage the engine, right? Because the engine gets confused. Okay, is this fuel or not? I have to deal with this water, that sort of thing. And then, of course, I already mentioned, so building up on the wing or the body of the plane, which decreases lift, increases drag, which is air resistance, and can stop the plane from flying. So icing is very, very dangerous and important to know about. Cool. So we have three types of icing. We have clear ice, which, as it sounds like, is just a nice transparent layer of ice, so glassy. And that usually forms in a really dense cloud or freezing rain. It spreads really unevenly over the wing and tail. And so this is when, and the reason why it's so clear and glassy and doesn't look like frosty is basically because the super cold water droplet, it only partially freezes on impact, but basically it has enough time to spread over a lot of the plane or a lot of the surface before it freezes completely, and that's why it becomes clear and glassy. And so that's as opposed to rime ice. So rime ice is opaque and milky white in color. So this picture on this last slide, this would be rime ice. And so that forms when you're flying in a stratiform cloud, so like a stable cloud. And so, it says in the slide here, so it accumulates on the leading edge of a wing and then an antenna. And so most things that poke out, so at the front of the plane, right? Like the first part of the plane to encounter these water droplets. And the reason for that is because this ice will form immediately, because the supercooled water droplet is immediately freezing onto the first thing it encounters, right? Like the leading edge of the wing, the front of the wing in this picture. Cool. And then the last one is frost, which is just white, kind of crystally, almost looks like snow that's just sticking to the plane. And so this will form in clear air, so not in a cloud, unlike the other two, where you just get water droplets that almost kind of form into ice crystals. So it is basically snow, but it's very like thin snow that's like sticking to the plane. Yeah, and so it'll not be like as thick as clear ice or rime ice, but it can still be dangerous if you get enough of it on the plane. Cool. And then there's a few ways you can protect from icing. So you can have fluids, so just like antifreeze, and that can be through a couple ways. You can either put it on the plane like by hand before you take off, or what some modern planes have is on the leading edge, so the front of the wing, will have tiny little holes, like hundreds of them, where if you're in the cockpit, you can push a button and liquid will come out of these little holes during flight and coat the wing in this antifreeze liquid. You can have something that's called rubber boots, which is basically just a layer of rubber on the front of the wing, right? And what it does is it pulses during flight, so it moves a little, and that breaks off ice. And then you can have heating devices, so literally just, as it sounds like, they direct hot air from the engine, like into the inside of the wing, or yeah, and so you can also have it so that the antenna can heat up, for example, the pitot tube, which is one of the air intakes for the instruments, can heat up as well. So yeah, as you can see, they really take it seriously, because icing, for all those reasons we talked about on the last slide, can be super, super dangerous. Cool. Okay, so we'll just finish off by talking about turbulence. And we'll finish off, just I see we're coming up to 7:30. I know you guys have closing. So turbulence can be classified as light, moderate, severe, or extreme. And just to put into perspective, most turbulence that you've ever experienced, like in a passenger plane, the vast majority of it will be light turbulence. Extreme turbulence means like it's gotten to a point where the plane can barely fly, and you'll only really see that if you're like flying in the middle of a hurricane or something, or in the middle of a thunderstorm. So we have 5 types of turbulence. Mechanical, so that's just air moving over an uneven surface, so like a hilly surface, a forest, somewhere with a lot of buildings, right? And so obviously that's in lower levels towards the ground. We can have thermal turbulence, which is just uneven heating of the Earth's surface, right, on hot summer days. So the sun heats the ground, and then the ground heats the air above it. But if it does so very fast, you'll get a lot of turbulence moving vertically. You can have frontal turbulence. So we talked about warm and cold fronts. That's just one air mass going underneath or behind another, as we talked about. You can have wind shear, which can be caused by a million different reasons, but that's just a very sudden change in wind speed or direction, typically very isolated, and it can be, like I said, from a variety of reasons. Then lastly, you have clear air turbulence, which only happens when you're really, really high up, like in the jet stream, which is at the top of the troposphere. And so that's caused by wind shear from the jet stream, as it says there. Cool. That'll finish up our lesson on air and air masses and weather. Okay, sorry, I'm just looking in the chat now. How could you get around this? Sorry, do you want to just put what you were, reduces lift, increases drag. How could you get around this? Okay, so I assume we were talking about the icing. So we talked about those de-icing things in the next slide. Okay, so I see I've already kept you guys a little over. So thanks a lot for bearing with me. Sorry my camera wasn't working today. But I hope you guys learned something from the PowerPoint. Once again, I'm CV Vorman. This was EOM 436.02 air masses. And I'll see you next time. Thanks, everyone.